share his screen and start his presentation.
Well, first, thank you everyone for coming. Thank you, Krishna and Reddy, to have a very good summary of my journey. So today I'm going to continue that journey. And today I'm going to talk about the pore pressure. The concept of pore pressure is so important for geotechnical and geoenvironmental engineering. Even today, we still don't know a lot about it. So what I would like to do today is first to give a few examples of the practical challenge. And then I will look at what would be the conventional definition of the pore pressure. And also provide a general definition that will apply for the situation where the conventional pore pressure has not been able to account for. And I'll give some example on the impact of the pore pressure on soil property. Finally, I provide a few of my perspective, a sample for the future opportunity. So let's look at soils. Here I put a fine sand, this microscopy of the fine sand. You see that in this situation, we have three phases, liquid, water, and the vapor and solid. So under such a condition, that we will ask ourselves, what will be the pressure in the pores? That depends on where you look at that. If you look at the larger pore, pressure actually under the partially saturated condition is negative. So we have to be careful when we say negative, it means that less than the atmospheric pressure. Simply because soil like water, we call capillary, and they basically form this curved interface. And the pressure magnitude could be as low as lower than the atmospheric, about 0.1 megapascal. And those important thing is the practically we can actually measure that. Come back to how we measure that. If you look at the soil carefully, particularly in the porous water, if you go close to the particle surface, the pressure actually is not what we measure. Here's on background. Is okay? Can you hear clearly? Excuse me.
Yes.
Yes. Okay. Yeah. So if you look at the close to the particle, as you approach it to the particle surface, the pressure actually will go from negative to positive, and it can go as high as 1.6 gigapascal. So that's very, very high, and it's compressive. That even under the unsaturated condition, this occurs under both saturated and unsaturated condition. The most challenging part is that this is not measurable at the current technology. So for years, even though we speculate, even though we have some theory, for example, we have electrical double layer theory that will allow us to calculate the swelling pressure among the clay particle. We never been able to directly measure that. So that poses challenges, but we have other reasons also can cause. So let's give an idea how big the pressure of 1.6 compressive in soil. This is a situation under both saturated and unsaturated conditions. So imagine that if you are in the explore for a submarine called the Challenger to go to the bottom of the deepest ocean on our planet. You go to Mariana Trench, and that is about 11,000 meters. And also it's definitely higher than the Mount Everest. And at that bottom of that, the vehicle can experience a compressive pressure. And you can calculate that simply by the unit of weight of water, seawater, times that. That gives you 0.1 gigapascal. So I'm making a postulate that actually the pressure could be compressive of 1.6. That's a lot. So we wonder why the pressure near the particle surface is so high. And the possible reason is because soil is a material, has a lot of silicon oxygen hydroxide near the particle surface, because the imbalance of the electrical magnetic field, they can attract anything that called polar material. Water is no exemption. So that is the possible reason. And we go into that one. I will try to convince you that it's actually true. It's really happening. And so the pressure in soil could be as high as 15 times of the pressure on the bottom of Mariana Trench. So let's look at some of the example of outstanding challenge for our community. The first is in the physical property of the soil. And we always assuming that the pressure, the unit density of soil water is 1. That's how we calculate the phase of air, liquid, and solid. And we do the phase diagram. However, evidence actually in the last half century indicate that the pressure actually, both experiment and the theoretical evidence indicate that the pressure could be as high as 1.8 grams per cc's. That's very, very high pressure. We know that water is, liquid water is, we call it somewhat incompressible, although it is compressible, but it's so much that actually can go to as high as 1.8. And also the water is going to cavitate, particularly under partial saturated condition, where we have a negative pressure. So that is another, that will change the property because of the cavitation. Another important is about the soil freezing behavior. We know that if you have a pure water, you're going to have a freeze at about 0 degrees if you put the water at the sea level. But however, if you put the water into soil, the soil is not going to freeze. And actually you can go to as low as minus 22 degrees C without freezing. And that behavior puzzling people a lot. And there's a different kind of theory to look at why it's so. And one of the important things right now we think, and we actually put some into theory, is because the pressure. When you increase the pressure, the water phase will shift. We'll come back later for this aspect. Another area is geotechnical engineering. We know that we deal with expensive soil, very widely spread anywhere, because the expensive soil, what sometimes we call Mount Morinite or 2-to-1, is one of the Mother Nature's final product before they go back to subduction to recycle it from the wetting of rock. And the soil could expand the volume few times upon the wetting. We also know that if you do the reverse condition of a climate, drying condition, and those clay can have a crack, they can have a desiccation. So that is one of the very important things, and particularly in today's climate change, acceleration of climate change environment. Loess is another one. Sometimes we call collapsing soil, which basically the way we call collapsing soil, because simply we look at it when you put a soil, that type of soil, aeolian soil, under the wetting condition, at some point they're going to volumetric reduction, shrink. So that's also very important. And so that can be related to the pore pressure. The environmental application, and also array of them, and I just give you example. We are concerned about how the water and the chemical species migrate in clay soil. For example, if you use that for the bentonite material for a final cover of landfill, or you simply use a bentonite as a slurry wall to build to contain the contaminant, the waste. And we wonder what will be the flow. The flow, not only the flow of water, but also flow of chemical, because soil of clay has a lot of absorption, not only absorb the water, but also absorb the chemical, but also can actually feel, so we call it semi-membrane behavior. Another thing is the water in soil, we traditionally use a Darcy's law. However, that is in the large pores. When the water go close to the particle surface, they can have another phenomenon that well documented to some degree, start to quantify. It's called film flow. So they're basically creeping around the particle surface. Why it's so? So also very much related to the pressure. Biological activity. We know that the biological activity, the essential condition is the pressure and temperature. And if the pressure would be that high of 1 point something gigapascal, how the biological activity is going to be there. Biological activity has been recent years utilized for our benefit, for environmental, for geotechnical infrastructure. Energy transfer. So we know that energy transfer here means the water is, because it's the only matter that actually so pervasive and changes three phases under the near Earth environment, pressure, temperature. So evaporation, condensation, the exchange between the soil and our atmospheric, it has a tremendous something to do with the pressure that we have in soil. So I just give some example, and what would be the common thing for those problems that we try to handle that one? What is the denominator? So in terms of what we call the thermodynamic, how we quantify that, we deal with temperature, we deal with pressure. Under the case of a partial saturated, we all think we deal with suction. And we need to worry about the stress because we need to know the integrity of soil as well as for the strength, as well as the deformation and the water content, how much that would be. So if you look at that pore water pressure, what is pore water pressure? Is it the one we only measure, or there's something we missed? We always think about it, and actually in the theory right now, is under the saturated condition, it's going to be positive. Under the unsaturated condition, it's going to be negative. Is that true? Stress. We deal with stress, as I said, for two purposes, for engineering perspective. One is to understanding materials strength behavior. The other one is to assess the deformation. What is measured suction? I'm sure a lot of people here today already hear, or some people even use that so-called matrix suction. What exactly it is? Is the matrix suction we define today inclusive, or we only represent part of that? How to define it? How to define the suction? How to divide the matrix suction? And how we measure that? That is very important, because ultimately, if something is not measurable, then it will be difficult to be applied to the practice. Effective stress. Effective stress is the keynote, the keystone of soil mechanics. We want to know that again for the deformation. We want to know that for the strength, and how we define that, particularly under partially saturated condition. Water content. So commonly we use a volumetric water content or gravimetric water content. And the volumetric water content, in fact, it reflects the larger pores. As I mentioned earlier, if the water density varies within the pore, the water content concept using the unit density, unit weight of density as one may not be appropriate. So we don't know. Gravimetric water content, on the other hand, it actually reflects how much water each mass of soil you can give. It reflects the ability of a soil surface interaction with water better than the volumetric. However, how we deal with when the soil changes the porosity, changes the larger void. So those are the questions that we have to think about fundamentally. So let me come back to what we currently define, what we call the pore water pressure. That actually is very important because to lay out the foundation here. So what I put here is what I call the represent element volume of soil, the smallest we could have, because you can do sand, which is a millimeter scale. Gravel is bigger, and then silt, and then go to clay. So typically you talk about a 10 micrometer. That has to be what we call the represented elementary volume, IV, we call it. Basically, you have to have everything ingredient we have. In this case, we have a soil, we have water. In the case of partial saturated, we have air. Because any quantity we define fundamentally, the pressure, the temperature, and the stress, it has to be within this represent elementary volume. Then we can extrapolate and say, okay, you have one point, you have another point, that cannot change. So conventionally, if we have start with the saturated condition, how we measure pore pressure? We use a piezometer. Everybody know that. The piezometer concept, basically, you can see that we have the ambient atmospheric pressure. If you have a compressive pressure in the large pore, then you're going to rise that one. So that's called the head, piezometer head. And use that, you can simply convert that to pressure if you know the unit weight of water, which is unity in the piezometer. If you have a partially saturated condition, so we change it from saturated to partially saturated condition, we can use a so-called tensiometer. So what tensiometer would do is to fully take advantage of the ceramic storm. The ability actually would not cavitate under certain kind of negative. The certain kind has a limit, depending on what kind of ceramic you use. But you can measure under the situation where the larger pore has experienced lower than atmospheric pressure. From there, you can actually calculate what would be the suction, we call, no longer called pressure, commonly called suction, which is the same thing physically, meaning with the compressive pressure we talk about. Now, in the case of, so if we have a soil with certain kind of bulk concentration of chemical, for example, like sodium chloride, potassium chloride, so on and so forth, we can actually even measure the osmotic pressure, we call. And if we put a semi-membrane there, then you actually can, the semi-membrane basically its ability to let the water molecule, which is about 0.3 nanometer, to pass through. However, the block those larger cation, anion chemical dissolve in water. So that way we can establish a so-called osmotic suction, or sometimes called osmotic pressure, depending on which side you look at it. So here we can actually measure further what will be the pressure due to osmotic suction in this case, but due to the concentration in your soil, because the water is going to have tendency, fresh water is going to tendency to drag into that one under the equilibrium condition. So that is current we can do. The current technology we can measure, we basically most of the time it's a millimeter scale. I put it at the most is a micrometer scale. So that is something currently we can do. However, there's something can happen with soil. If you look into the very detail of here, in this case, we look into the sub-micrometer, quite a bit of things happen. So you have a soil solid, it creates an electrical magnetic field. Any kind of polar material go into that, like water, they're going to attract to that. When they attract that, they consequently, and they're going to reach the so-called energy equilibrium. When that equilibrium, it will accumulate a tremendous amount of the pressure. This is very similar to the atmospheric pressure we have. We feel one bar near the Earth's surface, and it will decrease exponentially as you elevate to higher. And then this is so-called absorption water, because this water, the reason that water will be here is simply because of this electrical magnetic field, and that encounter the water as a polar material. And then far away from that one is a traditional, what we call the larger pore water, is the one that we measure, I should illustrate on the left side, larger pore water. So those water could be under negative condition, which means they are lower than atmospheric. And because the existence of this curvature at the interface of the soil and water. So the consequence is you can have the atmospheric pressure as an ambient condition. Then because the existence of air-water interface, you go to the negative, and then remaining so for large part of the water content until you got very close to the particle surface. How close it is, that depends on how strong your ability of a soil absorption ability, I call soil softening potential. Somewhere between 10 to 100 water molecule. But that is very important. You may say, okay, 10 water molecule, it's only 3 nanometer. And our pores is much bigger, as I showed, that at least greater than micrometer. But remember that the clay we have could have a few hundred square meter per gram. So that make a huge, tremendous difference. And consequently, you will see that the water density actually changes from the unity, actually under the tensile conditions, it's slightly less than that, and to very high, 1.6, 1.7, that magnitude, because of the ability of absorption. So here we are, we measure the difficulty part is that we use the conventional method to probe the pore air pressure, to probe the pore water pressure. we call actually the capillary pressure. And we define the matrix suction so far by the pressure difference between air and water. In fact, this is only talk about the energy due to the interface of air and water, not generally matrix suction. Now, what's the problem with that one? Because if we use that one, how are you going to determine whether your water in soil is in the solid or vapor or liquid phase? We go back to this water phase diagram. This is a very simplistic water phase diagram. Talk about the, at a certain temperature, pressure state will be in the liquid. At a certain will be a vapor and could be in the ice, we call solid. Now the temperature generally we can measure that one. It's pretty good, pretty accurate, and it actually is less subject to the scale issue. However, the pressure is very much dependent on the scale we talk about. If you measure in the larger pore pressure, it does not reflect the near the particle surface. That is one of the big problems. But here we're demanding that we need to use a true pressure to determine the water phase, universal, anywhere on this planet, in some other part of the space. This is the same thing for the phase diagram. So I'm throwing three very simple questions. One is is matrix suction equal to negative pore pressure? At the moment, my colleague or community in large think about, yes, it is. But in reality, the answer is it's only part of the capillary pore pressure. There's absorption I start to introduce. But why the pore pressure varies so much? Because of answer is because of the absorption. Because the existence of absorption. And can we use the matrix suction that we define here, that use the difference between air and water to look at the phase to determine what will be the phase the water will be in? The answer is no. So what we're going to use? We have to use the local pore pressure. This is another new, actually has been almost a century. Back to 1920s, people realized that the soil's absorption ability can change the pressure tremendously. Most people study geoenvironmental, geotechnical. We know that you can use the double layer, which is one of the theory, which is one of the absorption, not all of them. In fact, the double layer is one of the weak one for the absorption force. I mentioned about other force. So how to determine this local pressure? And more fundamentally, what are they and where they come from? So that's what I'm going to talk a little bit more. Now, before that, I also want to show you a little bit more about this phase diagram to understand what kind of pressure and temperature environment that we are encountering near the Earth's surface. So here we have a temperature, here we have a pressure, we have to use a true pressure. The phase diagram of water actually is not as simple as the one I showed you previously. In a certain region, this is the area we call metastable, which means they actually can change the phase, but it's not very stable. For example, we see the cloud. You notice that actually cloud actually changes the shape all the time. It's not very stable. So cloud actually is in the vapor form that transform from liquid to vapor most of the time. Of course, it can also come from ice, depending on temperature. But you see that actually they are not very stable. In a sense, they can condense to liquid. They can actually also become a solid ice if the temperature drop very fast. So this is called a metastable condition. But when you really reach the stable condition, you don't see the cloud, because it's just like nitrogen, for example. Oxygen, nitrogen, we don't see the cloud of nitrogen, we don't see the cloud of oxygen, simply because our temperature regime on the Earth environment, they all become very stable the phase relation. But if you go to Mars, you go other places, actually you can see the clouds of nitrogen and oxygen or CO2, for example. So this is the regime actually complicate our case. Now, if you look at the careful, the region that where we are dealing with temperature pressure for soil, water, under such a condition, we typically experience minus 30 degrees. Sure, there's some place on the polar could be lower than that, but most of the time, it's minus 30 degrees C to positive 60 degrees C. But of course, it can also go exceed, just give a range here. And under such a condition, you can have the pressure from negative 0.1 megapascal to the compressive 1.6. The negative comes from the fact that the clay material is very small. So we know sometimes we call the air entry barrier, which means that the larger pore actually can sustain the pressure lower than atmospheric. And if you drill a borehole, you find that it's called a capillary fringe above the water table. And that is where that we talk about this negative pressure. Now, if under in-situ condition, the temperature is the same, but however, the pressure actually can go to as low as somewhere about the 15 times lower, so minus 15 megapascal, because of the existence of the capillarity. But and then some point it's going to have a cavity. It's going to go to this metastable. So I probably this is the reason I don't have the access to go all the way up there because it is only to 200 megapascal. As I said, it can go to compressive 1.6 gigapascal. So the difficult part again here is the capillary pressure. We know that we can use a piezometer, we can use a tensiometer to measure that. But what about the absorptive pressure? How we measure the absorptive pressure? This is the part of the problem. We don't even have a theory until very recent. So let me give you an example of what happened in soil to kind of try to put every mechanism we can have to change the pressure. If you think about you are one of the water molecule. So I have this 1 nanometer size of martini cup. And we wonder about that at some point here, I call X, what will be the pressure? What will change the pressure in the martini cup? So let's look at how we define the water pressure. Water pressure is basically an average of inter-water molecular force per unit area, right? So water pressure, in the case of what we call the soil water potential, it's a part of soil water potential. We know that the other form also could be transferable, for example, like gravity. That can also be the water pressure. It can also be part of water potential. Same thing, we give example like osmosis. And the capillary pressure we define is basically the pressure difference between air and water. If you look at it, there is an interface between that one. If it's a flat surface, then you don't have the pressure deficit across the interface. Now let's look at what with the pressure. So basically, the pressure is a function of the salinity you have in the larger pore, the distance that you are away from your solid soil, and how much water content you have, because under unsaturated condition, they can change a lot of these concentration. They can also change the absorption's conversion, gravitational force. So if you look at that one by one, if you have a concentration, then you're going to change the osmotic pressure. Because the existence of solid particle surface, you're going to form the negative charge surface. A negative charge surface is going to interact with your liquid, and it's going to cause so-called electrical double layer together with your ambient concentration. So certain kind of electrical magnetic potential is going to convert to pressure. Also, because the solid is going to interact with your polar material, it's called a van der Waal. In this case, is between the solid and the water. That potential exists there no matter whether you have water or not. However, it will convert it to the pressure. So it's going to increase the further pressure, sometimes called disjoint pressure in the interfacial science. Hydration, we know that the soil has an exchangeable cation. We know the surface of soil is dominated by the oxygen and the hydroxide, the ions, and then also can attract water, orientate the water direction. So we call hydration. And then we have a conventional one that if you have unsaturated across the interface, then depend on the curvature, depend on the pore size, then you can also have the capillary pressure. And finally, the gravitational one, which is the one that we are living anywhere, anytime on planet Earth. So all these components, so I highlight this one, this four pressure has some common thing because each of these terms, it's electrical magnetic in nature. So these are the potential. This potential exists near the soil. Doesn't matter whether you have a matter around them or even in a vacuum, because it's just the electrical magnetic field, like the Earth electrical magnetic field. However, if we have water molecule close to them, they're going to convert it to what we call the pore pressure. So this four is a common thing that under the electrical magnetic and then convert to pore pressure. The issue we have here is how you connect the two. That is what we have been struggled, I would say, in the last century, since we recognize the absorption ability. And that is something I'd like to go further to look at that. So to define the water pressure in a sense that we can include all those mechanisms, that we can actually define the pressure in soil into two components. One is due to the capillary, just simply follow the mechanism. The other one is due to absorption. The capillary one is a mechanical interaction of the surface tension with the soil and with the water. So it's an energy directly through the mechanical energy. However, the one that we call absorption pressure that I alluded is due to the summation of these four different electrical magnetic waves that provided by the soil due to the absorption. So the two mechanisms. Notice that basically, if you want to know your pressure distribution in your soil, it depends on which point that you're interested. I put an X, which is use the soil particle as a surface, because all these components are dominating by the distance of X. Also, the second one is water content. You have a dry, you have a wet, because this water content actually is the one that actually convert how much the energy of electrical magnetic to the interparticle pressure. So that is a very concept that we put layout here. So notice that this pressure actually exists under both saturated and unsaturated condition. As a matter of fact, if your soil is saturated, all the electrical magnetic energy is already converted to the water pressure, which is at the moment our human being just not being able to get a very solid grasp like what we probe for the larger pores, tensiometer or piezometer. It's there. Give an example is that why clay has a cohesion. That's because under saturated condition, we talk about saturated condition. All those electrical magnetic field, it convert to what we call a conventional called cohesion. So that is the very reason this electrical magnetic field exists in there. The key here is how we can convert the electromagnetic, all these components, into the pressure that we're interested in. Now, one of the very important, I call the breakthrough, I'm going to talk about four breakthrough here today, is that by summating all these mechanisms, we no longer need to know exactly each of them. For example, we have a well-built theory of the electrical double layer for these two terms. But then how we going to do a practical problem? But here, because they're all electrical magnetic, so we can call them soil soft potential. It's electromagnetic. It's a matter how much they can convert it to the pore pressure. So that's very important in the conception that we can do that. Now, exactly how we do that. So we can use the unitary definition or way to unify what we call the matrix suction. So to do that, look at that. Here is the soil water REV for any kind of soil. And look careful, you have absorption water and capillary water. And that is how we define it here at this level. It's how we use the so-called Laplace-Young equation or Young-Laplace equation to figure out what will be the capillary pressure. But each of them, if you look at the scale, if we really want to define the pressure, each of them, the pressure is a very small intermolecular scale. And the same thing for soil soft potential that exists in vacuum, basically, or some kind of a dielectric material or non-polar polar material. How we connect that one? The way to do that is we use the energy equilibrium concept. So in other words, so-called the local thermodynamic energy equilibrium. Basically, if you look at that one, I would say that if the system is under equilibrium, then any point that you poke, the total head will be the same. Whether you go too close to the particle surface or whether you are away from to the air water interface, or even you go to the air phase. So if you apply this principle and you put all the absorption ability into one term, and then the pressure differences developed by both capillary and absorption, and you put all the terms together, this is a so-called total head. And then you impose the total head will be same anywhere in this soil. And you will find that actually matrix, what we call the matrix suction or matrix potential, which is the negative sign for that, which is truly reflected how low in comparison with the fresh water. is this equation. So basically, we are going to have absorptive ability. We're going to have a capillary, but we also have another part which is due to absorption. And the absorption is basically converting this energy to this one. But how much it convert depends on what kind of environment we're going to give it. In other words, what we call a matrix suction. In fact, it is interesting to look at the terminology because when we look at the first defined matrix suction, we think about that is due to the soil particle, which is true. But however, the equilibrium condition we are always looking at is whether the air humidity or whether it's what we call the suction environment. So in fact, this is the relation that we can completely unify, and it has two components. We can look at this one as illustrated here is, imagine that you have air pressure, then you have the cause, the decrease of the pressure because the air-water interface. So under that condition, we have a matrix suction, this value, which will be the same, doesn't matter where you go from the particle surface all the way to bulk water, to the interface. Now, under that condition and this equation that put here, it's simply state that you're going to maintain your pore pressure negative all the way until at some point where you're close to the absorption field, electromagnetic field, where the water molecule is going to interact with your soil particle. And from there, your pressure is going to increase. And your pressure is going to increase, you see that the differences here, and it's going to follow to your absorption potential. So that is the pressure distribution that we're going to see. And that is the one that I'm talking about at the beginning, that under any circumstance, whether it's saturated and unsaturated, you're going to have the pore pressure 1.6 gigapascal near the somewhere between, depending on the soil, near the particle surface. You can also look at a little bit more, very same thing to interpret that one is further decompose the pressure into two parts. One is due to the capillary, which is simply right in this bulk water. That is the traditional capillary pressure. That is actually we have defined by and large so far the matrix suction. And then the other part that is due to the absorption. Sorry. That is due to the absorption. Notice that is the conversion between the two. So exactly here that we actually can look at it as a capillary pressure and absorption pressure. Now the key here is how we determine this absorption potential. Well, we have a clue here. If we be able to determine the soil matrix suction precisely, then we will actually also determine the capillary pressure, then we will determine that. It's simply just like the equation I will give the analog to Tazaki's effective stress. We have everybody understand here that the effective stress is equal to total stress minus the pore pressure. Even though that the effective stress is not measurable, it's a soil skeleton stress. However, we'll be able to measure total stress. We'll be able to measure pore pressure. Therefore, we can quantify that. So same thing here is that we will be able, once we able to determine what is your soil subject potential. Once we do that, then we can solve the problem. So how to measure the soil water potential? And this is an equipment. It's revolutionary in my view, because before that, for most people who are familiar with the soil water retention measurement, it's only 10, 20 points. Each point takes a few weeks. But here you have this sweep through the humidity from 0 to 100, and then look at the water equilibrium and doing the wetting and the drying. And here is the mixture of the bentonite and the kaolinite material. You can see that they have a very different path. We call it hysteresis. You can also see that the degree of hysteresis is different when you have a bentonite material versus the kaolinite material here. The key here is that now we'll be able to measure this total potential with very accurate. Typically, you can get a few hundred of data measurement. So with this measurement, we actually can do something. So we can actually measure from this isotherm, so-called isotherm, sometimes called soil retention at high suction. You can know the specific surface area precisely, and you can even distinguish it between the surface of internal or external. For non-swelling soil like the kaolinite, you only have predominantly by the external particle surface absorption. For the expensive soil, you have both. And in fact, the interlaminar one could be more important, depending on the cation exchange capacity. We can also quantify that one from this isotherm. And we can quantify soil softening potential. That is very important because once we quantify the soil softening potential, we can come back to use the same unitary definition of matrix suction to come back to devise a way to directly quantify the pore pressure distribution under both capillary and absorption. So I'm showing you some of the way that we can do that right now. Is once you measure this experiment called isotherm, the soil water retention curve, the theory would divide that into two unambiguous parts, precisely absorption part of isotherm and the capillary isotherm. The capillary isotherm is one actually you can directly use a Kelvin's equation, for example, to find out pore site distribution. This is water. This is not using mercury or anything. So it's very much reflected exactly how the water and the soil interact with each other. The absorption part is the one that actually give us the clue that you can calculate what will be the pore pressure. So here's an example that we can use the theory to calculate for bentonite. That right here in Denver, that we find they call it Denver bentonite, which is basically mountain wallenite, very similar to Wyoming sodium mountain wallenite, except here is calcium dominated bentonite. So you can have a, depending on what kind of water content you want initially, you have soil water content. From the soil softening potential, because we can determine from this curve, we can calculate what will be your pore pressure distribution, depend on either you call the statistics done to the particle surface. If you think that is very vague, but you can convert that to the water content. So that is your pressure distribution. It can be very high. For this case, for example, it could be as high as highs of hundreds of megapascal. For expensive soil, in fact, you can further figure out the pressure outside the swelling pressure inside. In this case, we see that the swelling pressure, there's a barrier here, lower than certain kind of water content. The water is not going to be able to go. And from that, you're going to see the swelling pressure start to expand the interlayer, and the swelling pressure is going to continue to decrease until the water content is very high. So with this simply input of one experiment of isotherm, you're going to get us quite a bit of information, the pore site distribution, and you can get the pore water pressure distribution, and you can even know what will be the true swelling pressure inside the crystalline soils. So let me use a few minutes to talk about the impact for soil property. So in the last decade or so, we have worked on how that true pressure or local pressure impact the soil property. And here's an example that if you look at the soil water density, you can actually measure that by some of the new methods. In fact, even the old method of consolidation, the saturated consolidation, you can measure the pressure. And this is actually an example here. You can see that the water content density change. So from there, you can see that this is evidence because we measure the soil water retention, we spread it between the absorption and the capillary part of the retention curve, just like isotherm. And you see that there's a correlation between how the water density is going to change. It's going to increase in this case due to the absorption. We can also look at the so-called finite strain modular, called elastic modular. And the retention curve here, you see that you can spread it between absorption water and the capillary water. And by the same token, we conduct an independent experiment, you will see that the modular change actually can also be spread between the hardening due to the capillary and due to the absorption. So these are the experiment evidence indicating the importance about this pore pressure, how they're going to impact the fundamental soil property. Small strain, which is very important to look at the seismic wave. And again, the same information that you can see that changes. And here's another example is the soil freezing curve. The soil freezing curve, just like the soil water retention curve, is very characteristic for each soil. And actually 1/3 of the land of the earth that covered by the soil that's subject to freezing and thawing. And this phenomenon, actually, you can see that using this is 0 degree, and then here basically is the horizontal is the liquid water content. So here the larger pores of capillary water start to freeze. But however, there are liquid remain because of absorption. And that actually you can see that very much correlate to the experiment data of soil water retention that spread between absorption water and the capillary water. Another example is thermal conductivity. So thermal conductivity, they conducted in a way that not only depend on the particle dominating by particle size, particle contact, but also how much absorption water, particularly near the contact area. So you see that because of the absorption, generally the thermal conductivity, it varies less compared to the granular material like sand. But that also can be correlated to the study of soil water retention, how much absorption water, how much capillary water, and each of the rows corresponding to the thermal conductivity. Another very important is the one that I've been working on a long time is how we can unify the effective stress under both saturated and unsaturated condition. So I look at very quickly review that the current paradigm. Common one is the so-called Bishop, which basically draw the very element REV level of the stress. And it basically consider the total stress and the capillary pressure, because as you see that Bishop defined it's an air pressure minus water pressure times a coefficient. So that is only the capillary pressure. So that's a stress because it's upscale from the matrix suction, which itself is not a stress quantity, to the stress quantity, but it's only capillary. Also very popular paradigm is so-called two independent stress variable. As you see that each of them, this one is only capillary pressure, but it's not a stress. The way that we define that here, we use a unified way, it's so-called a suction stress. So we no longer say just like a Bishop capillary. We call it suction stress, and the suction stress has two components. Explicitly, they can express by suction stress of absorption components and the suction stress of capillary components. And each of those is clearly defined by a simple equations here with the 6 very clear physical parameters. In fact, that all these 6 parameters are somewhat independent. That is why we find some kind of minimum, but each of them has a very different physical meaning. For example, if you have the largest, this parameter, it's your porosity, relate to your porosity, how big it is. And here you have the, what's the maximum that you can absorb the water. And then if you have a dry, when the soil, particular clay is dry, what is your maximum suction stress? So we can unify that further. So finally, I'd like to use a few minutes just to talk about what I feel the opportunity for us to moving forward. We put into 3 categories. One is the soil density. Also, no, the first is about the soil physical property. The physical property can be subdivided into soil water density, how the phase is going to change, specifically gravity, because even at the moment, I'm still doing research. I don't know the definite answer. Even the soil water density could be so high, how much it would impact our phase diagram, right? So how we can measure the soil surface area. Right now, the common practice is to use EGME, for example, which is not a water material, but even though it's a highly polarized material, but it's not a water. So the interaction with water, use that to probe the surface area may not be as accurate as the one directly used to water. Cavitation is one very important phenomenon in soil because I show you that the diagram, the region that where we are going to the so-called metastable region. And the metastable region has a lot to do with the very small perturbation of other factors than the thermodynamic quantity of temperature and pressure. For example, you have impurity a little bit, tiny bit, and it will actually change your entire phase change. Freezing behavior, how we can develop a better way to quantify the soil freezing curve. The other part is geotechnical. I just give a few examples. Expensive soil, mark cracking. Mark cracking is pervasive, and particularly under the accelerated climate change environment. Somewhere it's very dry, somewhere it's very wet, and then most of clay. Under the field condition, it will likely to create a crack. How we characterize that? How we use those new concept of pore pressure. And then loss behavior, the change of the volume upon the wetting. And finally, about the geoenvironmental, which most of the audience here are very concerned. And basically, in the three categories I put here, the flow and transport, how the water is going to interact with the soil, how the chemical is going to interact with water, interact with the soil. And that has a lot to do of this, the equilibrium pressure and the film water particular, because they are attached to that. And there's some indication of over the years that the film water cannot be well described by Darcy's law, for example. Biological activity, pressure, temperature, it's the key, particular pressure, whether living beings in soils, how they live. And energy transfer, evaporation, condensation, one of the I would say poorly understood established field is how the air and atmospheric and the soil interact each other. In other words, the evaporation. What control the evaporation condensation rate at the land surface? So those are the a few of the my perspective for you guys. And finally, I'd like to make a conclusion for my today's talk. I will summarize in a few points. The conventional pore pressure we present, so far we know we can measure and use it in the practice is bulk pressure, or we call it capillary pressure. Basically ignore the local pressure due to absorption. And it is inadequate, as I show you some of the soil properties, very much depend on that. The absorption-induced pore pressure, this is very localized, but it could be very high. It could be as high as 1.6 gigapascal, or even as 15 times more compressive, high pressure than the bottom of Mariana Trench. And it actually exists in both saturated and unsaturated conditions. But we can do that by unifying the concept between suction, negative, positive, by unitary definition of matrix suction, which basically explicitly divide the matrix suction into a capillary pressure, which is conventional one, and the absorption one. And all you can write it simply is the basically two part. And then we can use the experiment method to quantify that one, using the soil water isotherm to quantify that. We can basically predict the pore pressure distribution for any soil under any water content once you measure the soil water isotherm and using the unitary definition of the theory. The absorption here today I'm talking about induced pore pressure has a profound impact on the engineering property, soil property, fundamental property, and the geotechnical engineering property, as I show you today. Thank you. Thank you all for your participation.
Thank you so much, Professor Liu. Wow, that was